Hello, everyone. My name is Yifan, and I'm coming from Caltech. It's a pleasure to have the chance to present here, and my topic is consistency of hierarchical parameter learning, empirical Bayes and Kernel Flow approaches. This is joint work with Andrew Stewart and Herman Awadi at Caltech. Let's get started. We first give a reminder of Gaussian process regression, the GPR. We are in the context of supervised learning. There is a function U dagger, and we observe its pointwise values, yi equals U dagger xi, I from 1 to n. We assume a loss-free scenario. The target is to recover U dagger from this data. The GPR solution to this problem is as follows. First, we give some compressed notation. We use cosine dot theta as a Gaussian process with mean 0 and covariance k theta. Theta is a hierarchical parameter. K theta being a covariance operator, it can be seen as a function from d times d to r. We use the green x as a collection of all data points, x1 to xn. And the U dagger x means U dagger applies component-wisely to each element in x. So this quantity is a vector of dimension n. Similarly, k theta xx will be a matrix with dimension n times n. In the same way, k theta dot x will be a collection of functions with entry k theta dot xi. Finally, the GPR solution U dot theta x will be given by the conditional expectation of cosine under the observation. It has the following explicit form. It depends on three important things: the kernel k and the parameter theta, the data set x, and the truth U dagger. Because they are important, we use colorful sign to highlight them. That is Gaussian process regression. So what's the problem? As all we know, Gaussian process regression can give us a solution that completely agrees with the truth on the data set if we are in the loss-free scenario. That's to say, for any theta, we can get a solution that achieves zero training loss. However, in practice, we are often more care about the out-of-sample error or generalization error. In that case, how shall we pick the good theta? This is a model selection problem. We need to learn a good hierarchical parameter theta from data. The following is the roadmap of this talk. First, we will discuss two approaches to this problem, the empirical Bayes approach and the approximation theoretical approach. Then, we will compare the property of the two different approaches, especially their consistency as the number of data goes to infinity. We start with the Bayes solution. Bayes' perspective is to put everything in probabilistic way. So we put a prior on theta, and we assume the U dagger is a Gaussian process. Then, using this probabilistic model, we can use the Bayes rule to calculate the posterior. If we adopt the empirical Bayes, the EB perspective, and we assume the uninformative prior on theta, then we get a point estimator theta EB given by the mean measure of the following EB loss function. It will be the elective log likelihood of some Gaussian measure. Essentially, it's doing maximum likelihood estimate. The EB solution will depend on the dataset X and the ground truth U dagger, so we write them explicitly here. The Bayes solution assumes the prior distribution on the quantities. This may be brittle to model misspecification if the model is not the case. Alternatively, we can think about this problem in a more straightforward way. We set up our goal and we choose a cost function d. Then we pick up the theta as optimizer of this loss function, which is the distance between the ground truth and our estimated GPR solution. This is quite natural and ideal. However, U dagger is not available to us, but we can approximate it. As one example, we can turn to minimize the following problem. This is the distance between the GPR solution using the whole dataset X and the GPR solution using a fraction of the dataset, which is pi x. Pi is the subsampling operator. This problem is similar to cross-validation because we are using a fraction of this data to infer the property of the original data. Here, we are especially interested in a specific choice of D, which is proposed by Awadi and Yu in 2018 in the work of Kernel Flow. The Kernel Flow loss function is written as follows. We compare the distance between the two GPR solutions in the sense of k theta long. K theta long is the RKHS norm determined by k theta. And we normalize it by the norm of the first one. We can interpret this KF loss as follows. A kernel will be good if subsampling data does not influence the GPR solution much in the sense of the RKHS norm. It's also quite natural. So we have two different algorithms and two different estimators. The question we're going to ask is that how do they behave as the number of data goes to infinity? This is a consistency question. And in this work, we will answer this question for some specific models. To begin with, we introduce the setup of our specific model. We consider the domain to be a torus in d dimension. That is, it's 0, 1 to the power of d with periodic boundary. Our data is equidistributed on this torus. It's on a lattice with match size 2 minus q. So it's in d dimension, so the number of the data will be 2 to q times d. The kernel family we are considering is the Martin kernel with the regularity parameter to be inferred, and that is t. So the theta will be the parameter t. In the KF loss, we need to introduce a subsampling operator. Here, we choose pi to be the projection from xq to xq minus 1. Under the above context, we can have the following theorem regarding the consistency of the two estimators. It says that if your dagger is drawn from the Gaussian process with mean 0 and the covariance minus Laplace to the power of minus s for some s, then as the number of data goes to infinity, we have the EB estimator converge to s, and the KF estimator converges to an interesting limit s minus d over 2 over 2. The convergence is in probability. To convince you this theory is correct, we present a simple experiment here. Consider one-dimensional case and s equals 2.5. The number of data equals 2 to the line. And we use match size 2 to minus 10 to discretize the Laplace operator. On the left-hand side, we output the loss function of the empirical Bayes approach for single realization of your dagger. We can see that the minimizer will be 2.5, matching the prediction. On the right-hand side, we have the KF loss. The minimizer is 1, which is also matches the prediction. Moreover, there are some patterns in the loss function. For example, when t is less than 2.5, the EB loss will exhibit a linearly decaying tendency, but when t is larger than 2.5, it blows up very quickly. However, for the KF loss, it's more symmetric behavior. The message is that our theory in this paper can completely predict the behavior shown in the figures. Okay, hope I have convinced you that the theory is correct. And now we are going to ask another question, which may be even more interesting and important. That is, why do the two algorithms converge, and how are the limits special? This is related to the question of implicit bias of different algorithms in learning parameters. To answer this question, we turn to look at their L2 population errors or L2 generalization errors. In our first experiment, we adopt the same setups as before. We choose the number of data 2 to the q, and we vary the value of q. We compute the population L2 loss, which is between the U-dagger and our GPR solution. We average it over the Gaussian process to make the figure become nicer. The below is the output. The x-axis is q, and the y-axis is L2 error. We can see that as the number of data increases, for different choice of t, the generalization error will decrease. As t goes from 0.5 to 1, the slope of the convergence becomes sharper, which implies the convergence rate becomes better. However, when t passes through 1, the slope rarely changes. That means t equals 1 is a minimum t that suffices for the fastest rate of the L2 error. That will be the implicit bias of the kernel flow algorithm. Then we fix Q equals line and still compute the L2 generalization error. The below is the output. We can say that T equals 0.5 leads to the minimum L2 error in this average things. And T equals 0.5 will be the parameter that the empirical bias will pick. That's to say the empirical bias, the implicit bias of this algorithm is to pick the one that leads to the minimum L2 error. In summary, in this experiment, we observe that for the simultaneous kernel model, EB and KF have different selection bias. EB selects the T that achieves the minimum L2 error expectation, while KF selects the minimum T that suffices for the fastest rate of the L2 error. That's quite interesting. And in this paper, we characterize this implicit bias. In our work, we also made more comparisons between the two algorithms. Especially important is the robustness to model misspecification, because this may be the reason behind choosing different algorithms, because different algorithms can have different robustness to different model misspecification. Overall, the takeaway message of this work is that we are doing hierarchical parameter learning, and there are two approaches, Bayes approach and approximation theoretical approach. In our paper, we provide some theoretical analysis of the two algorithms for toy model, the Merton class model. Generally, it's of interest to compare them in more complex and realistic machine learning or inverse problems, and to explore more about their advantages and disadvantages. That's it. Thanks for your attention.